We will now discuss Newton's third law of motion, action and reaction. Newton realized that force is not a thing of itself, but a part of a mutual action, an interaction. Forces come in pairs. Whenever one exerts a force on a second object, the second object exerts an equal and opposite force on the first object. One force is called the action force, the other the reaction force. Simply stated, the third law says for every action there is an equal and opposite reaction. In other words, I cannot push on you if you do not push on me. Sometimes determining the action and reaction force is not simple. The poor bug that hits this speeding bus's windshield may splatter everywhere, but the force that he applies to the bus is equal to the force that the bus applies to him. To identify the pair of action and reaction force, although it may not be obvious, there is a relatively simple recipe to do so. Identify the interaction. Let's say that object A interacts with object B, then object A exerts a force on object B as the action, and object B exerting a force on object A is the reaction. Now in this situation, the action and reaction forces are simple to identify. The bat hits the ball hits the bat. The force of the ball on the bat is the same as the force of the bat on the ball. Here, the foot is applying a force to the ball, and the ball applies an equal and opposite force on the foot. Action and reaction forces. Now the bird pushes down on the air below, and the air pushes the bird up. In these next few scenes, see if you can pick out the action and reaction force. Now what about action and reaction on forces that have significantly different masses? When a boulder falls to the earth, the boulder pulls up on the earth with as much force as the earth pulls down on the boulder. The forces are equal in strength and opposite in direction. Although the pair of forces between the boulder and the earth are the same, their masses are quite unequal. Yes, we do not feel the earth being pulled up by the boulder. Similarly, when a bullet is fired from a rifle, there is an interaction between the bullet and the rifle. The forces are equal and opposite, so the rifle kicks. But due to its smaller mass, the bullet accelerates much faster than the more massive gun. A rocket engine and the recoil of the gun accelerate because of the reaction forces created by the bullets they fire. In the case of the rocket, air. Now let's examine if action and reaction forces cancel. In this picture you see an apple pulling an orange in a cart. True, the force of the apple on the orange is equal to the force of the orange on the apple. according to Newton's third law of motion. So, how does the orange ever move in his cart? Is the apple wasting his time? Not really. We must look at the entire system, not only the apple and the orange in the cart, but the relationship between the apple on the ground and the cart on the ground. As long as the orange is sitting in the cart and the apple has his feet on the ground, when the apple applies force to the ground with his feet, and that force is greater than the weight of the orange in the cart and the friction of its wheels on the ground, then the cart will move forward. So when you look at merely the orange and the apple as a system by themselves, then yes, the action and reaction forces cancel. But you must look for a force outside the system, such as the force of the feet of the apple on the ground, in order to determine if the force is enough to make the cart move. The horse-cart problem is a paradox that helps us understand this relation between action and reaction forces. The farmer told the horse it was pulling his wagon to start moving so that he could go to market. But the horse, however, says, I can't, because there is, according to Newton's third law, an equal and opposite force from the cart on me, so I can't move. No matter how hard I pull, I can't take you to market. If we look at just the horse and cart as a system, then it's true. These forces do cancel out. But as we discussed in the situation of the orange and apple, the horse has the same problem. As long as he can apply a force to the ground that's greater than the weight of the cart against the ground and the resistance of the wagon wheel against the ground, then he can indeed move the cart forward. Although the forces of action and reaction between the horse and the cart will cancel, once we look at the entire system, including the ground, we can see that the horse can accomplish his task of taking the farmer to market. If you were to take your hand and hit the wall, obviously it would hurt your fist, because the wall exerts a force on your hand equal to and opposite the force that your hand exerts on the wall. Just as in this picture, the car exerted a force on the wall exerted an equal and opposite force on the car. The object that the force is applied to must be capable of supplying a reaction force equal to the force that it is being hit with. If you hold a piece of paper in front of you and you take your fist and you hit it as hard as you can, the paper is incapable of supplying a reaction force equal to the action force of you hitting the paper. This is where the old saying comes, you can't fight your way out of a paper bag, because that paper bag does not have the ability to provide a reaction force equal to the action force that you place upon it.